Hello everyone, my name is Dianisa Khoirum Sandi. Here I would like to present part of our research with the title of Photocatalyst Comparasion of Light Mn-doped strontium titanate. Here our outline. We all know that Indonesia has a great number of textile industries. And nowadays, not only Indonesia, but the world is facing many environmental issues, one of which is water pollution. One of the sources of water pollution is dye wash from the textile industries. And one of the dyes that is commonly used for the industry is methylene blue or MB. We know that the effect of water pollution is very harmful in environment, aquatic life, and of course the human life. And these are the several efforts we can do to reduce the water pollution. But for the water pollution from this was from industrial activities, researchers has conducted research with various methods. One method that attracts the concern of the scientists is photocatalysis. Photocatalysis is one of the advanced solution process that is employed for oxidative elimination of micropollutant in the water pollution treatment. It uses light energy from sunlight, UV light, or microwave to degrade the harmful water into the harmless water, and it uses the help of photocatalyst material. For the illustration, the photocatalysis process is like in this picture in the laboratory. And several photocatalyst material that is commonly used to study is zinc oxide, titanium dioxide, ferric oxide, strontium titanate, or SrTiO. SrTiO is gaining much attention today to be the photocatalyst material because it has excellent structural stability, photocorrosion resistivity, chemical stability, and structure tunability. SrTiO is one of the perovskite material, and it can act it can act as semiconductor material if it get some treatment. It has a cubic structure, and doping with a metal into the SrTiO structure can improve the photocatalytic properties. And among the available dopant, manganese doped strontium titanate is preferred here because manganese is unique. It can act as Mn+2 or Mn+4 to replace either strontium or titanium side. Several studies has conducted the synthesis of Mn-doped SrTiO at high level with several methods and various sintering temperature to investigate the doping mechanism on SrTiO structure. Here we think that it is necessary to further explore the synthesis process so it can maximize the application of SrTiO. So here, the aim of the study is to synthesize manganese-doped SrTiO with low manganese doping, which is 1% and 3% using the co-precipitation method, and to compare and determine the effect of low manganese doping on the photocatalytic activity of manganese-doped SrTiO as photocatalyst for degrading MB dye. These are the material and tools we use. For the procedure here, we use a co-precipitation method with the general formula of manganese-doped SrTiO is like this, where X is manganese concentration, which was 1% and 3%. This is the procedure for the fabrication. First, oxalic acid, dihydrate, and strontium nitrate were separately dissolved in isopropanol, and the two solution was mixed to become this solution, and separately titanium tetraplutoxide and manganese nitrate tetrahydrate were mixed in isopropanol, and the three solution was were mixed to get the solution of Mn-doped SrTiO, and the solution was then deposited for 24 hours, and it was then hydrolyzed at 100 degrees Celsius for 6 hours and to get the powder of Mn-doped SrTiO. And finally, the powder was sintered at 1000 degrees Celsius to get the final powder of Mn-doped SrTiO. After that, the powder was characterized using XRD and FTIR to analyze the crystal structure and chemical bond, and further to confirm the formation of Mn-doped SrTiO. And then the photocatalysis activity was evaluated. Follows like this illustration. So first, the solution of methylene blue and Mn-doped SrTiO was made, and it was then irradiated under UV lamp for a certain time. After that, after certain time, it will make degraded MB. The degraded solution of methylene blue was then tested using UV spectrophotometer to get the absorbance and then to calculate the percentage of MB degradation. Here, the irradiation time was varied from 0 until 6 hours. Figure 1 shows the XRD pattern of the Mn-doped SrTiO. The pattern match with the ICDD database for SrTiO. Second, there is no manganese compound in the pattern, and third, the peak shift. These three show that the doping has been successfully conducted. Next, table 1 shows the lattice constant, cell volume, crystalline size, and lattice strain of Mn-doped SrTiO. Here we can see that lattice constant decrease with increasing manganese concentration. It indicates that manganese act as Mn plus 4 that replace titanium plus 4, which it has a smaller ionic radius than titanium, so the lattice constant decrease. Automatically the cell volume also decrease, and here the crystalline size increase, which means that the higher doping promote the growth of crystal, and the lattice strain also increase with the higher manganese concentration, which means it is because the insertion of more manganese, more ethyl, more manganese, or more material more foreign material into the SrTiO host structure. Next is the FTIR spectra of Mn-doped SrTiO. Here we can see that below the prominent peak here below 1000 below 1000 is correspond to the strontium titanate crystal lattice vibration, and specifically the band at around 850 and 560 is the stretching vibration of strontium and oxygen chain and titanium and oxygen bonds. And the band at around 1460 is correspond to the vibration of carbon and hydrogen chain, and then the band at around 1760 is the bending vibration of carbon and oxygen double chains, and then the band at around 3400 is the strain vibration of hydroxyl lattice from titanium and hydroxide, or by strontium and hydroxide chains. Here we can see that there is a carbonate compounds and no manganese compound vibration. This result, FTIR results, agree with XRD result. Next is the figure 3A and 3B is the absorbance spectra of the degraded methylene blue by Mn-doped SrTiO photocatalyst, and figure 3C is the degradation percentage of methylene blue dye. From figure 3A and B, we can see that the absorbance peak apparent at around the wavelength of 500 until 700. And next, from these two pictures, we can see that the longer irradiation induces more degraded MB dye, so that the absorbance value decrease. It is because the longer irradiation time, the more chemical reaction happen, so the more degraded MB, so that the absorbance value decrease. Next, from the figure 3C, we can see that at 0 hours irradiation, the degradation percentage of Mn-doped SrTiO3% 3% is higher than 1%, but after 1 hour's irradiation until 6 hours irradiation, the degradation percentage of Mn-doped 1% is higher than 3%. So here we can conclude that the best photocatalytic activity is achieved at Mn-doped SrTiO 1%. Why? It is because from the literature review we get, the increase in the doping concentration means there is a possibility of mixed occupancy of sites, since acceptor level generate to the reaction of photogenerated charge carrier, so that it decreases the degradation rate. So the photocatalytic activity of Mn-doped strontium 3% is lower than 1%. Finally, we can conclude here that the synthesis of Mn-doped strontium titanate with a low Mn concentration has been successfully conducted using the co-precipitation method, which is confirmed by XRD and FTIR data. And then we can from the photocatalytic test, we can see that Mn-doped SrTiO photocatalyst at a low Mn-doping concentration has successfully degraded MB dye under UV irradiation. And then we also see that the degradation percentage increased with the longer irradiation duration. And finally, we can conclude that Mn-doped SrTiO 1% showed a better photocatalytic activity than Mn-doped SrTiO 3%. Thank you.